Welcome to all of you. In this lecture, we are going to discuss about the ray theory transmission, within which there are three topics, out of which two are covered in this lecture. They are total internal reflection and the acceptance angle. So let us start with the ray theory transmission. There are few concepts which we had already gone through, and just for the sake of recalling, we are going to have these terminologies or the sentences. First one, the propagation of light within the optical fiber makes use of the ray theory model. The refractive index definition. The refractive index of the medium is defined as the ratio of the velocity of light in the vacuum to the velocity of the light in the medium. Few more to remember. The refractive index of the core is always considered as N1. Refractive index of the cladding is always considered as N2. Core will have the always higher refractive index and the cladding will have always the lower refractive index. The optical signal, also known as the light signal, travels in the core region of the optical fiber. Now let us have definitions for the two terminologies. First one is the critical angle, and in the next one we are going to have for total internal reflection. So critical angle, the angle of incidence at the point at which the angle of refraction becomes 90 degree is called the critical angle. So it is represented by the term phi c, and its equivalent equation is phi c is equal to sine inverse of n2 by n1, where n1 is the refractive index of the core and n2 is the refractive index of the cladding. We'll go through this in detail in the upcoming diagrams with more clarity. Now definition for the total internal reflection. If the angle of incidence is beyond the critical angle, the light ray gets reflected within the denser medium rather than causing refraction. This is called total internal reflection. So the term denser medium here refers to the core of the optical fiber. Now let us have a clear understanding of the terminologies, the critical angle as well as the total internal reflection via these diagrams. So we are going to have three different diagrams and this is the first of them. Now try to understand this diagram in a very clear manner. So high index N1, the index refers to the high refractive index. So this line and below is considered as the core of the optical fiber, and this line and above is considered as the cladding or any other medium having lower refractive index. So this is higher refractive index and this is the lower refractive index. Now take the consideration of the light which is traveling in the higher refractive index medium. Now this is the ray of light that is being represented. Now when the ray of light is going to have incident at the position or the interface of these two layers or these two different refractive index layers, then in this particular case the angle of incidence is known as phi 1, angle of refraction is known as phi 2, and the ray of light will not come back, rather it will get refracted to the another medium. So this is called the exit ray. So we are expecting to have a reflection, but due to certain condition, that condition we are going to refer next, due to certain condition, the incident ray will get refracted and it will pass through the lower refractive index medium. 100% will not go over here. A part, very small part of it will get reflected back to the same medium. Remember the terms, phi 1 is the angle of incidence, phi 2 is the angle of refraction. Getting into the second diagram. So in this case, same two mediums are being assumed over here. So in this case, the angle of incidence has been increased compared to the previous one. The angle of incidence has been increased. Now here we can observe that at the interface of these two separate layers, now the refraction is exactly in line with this interface. Now angle of incidence, we call this as phi c, and the angle of refraction is the 90 degree. So this is in line with that of the core cladding interface. So now this particular phi c is what we know as the critical angle. So now remembering the definition of the critical angle, in the simple understanding we say that, so critical angle is the angle of incidence at which the refracted ray will become 90 degree, or it will just glazes the interface of these two medium. So this is called the critical angle. Now coming to the concept of total internal reflection. So refraction is what we used to study in the previous two diagrams, and in this case we are talking about the reflection. So reflection in the sense, so after incidenting, if the ray comes back to the same medium, we call that as reflection. So again we can observe that the angle of incidence is very much higher than the previous case. So phi is the incidence angle and phi is the reflected angle. So that means we can conclude that if the angle of incidence is greater than the critical angle phi c, then in such cases the light will get reflected back to the same medium. Such type of waves we consider as the total internal reflection. Criteria is the angle of incidence phi, referring to this one, must be greater than phi c. Then only the total internal reflection is going to happen. Otherwise, it will not happen. Again, the criteria must be remembered. So the light is now traveling in a medium of higher refractive index, and it is going to hit an interface of lower refractive index over here and the higher refractive index. In such cases only we are considering the total internal reflection as well as the concepts of critical angle. Now these two diagrams and the relative explanation, you can just go through this. Again, you can just remember here. So this is of higher refractive index, this is of lower refractive index, and here the refraction is happening. That means light is escaping from this medium to another medium. Angle of incidence is phi 1, it is quite less. Therefore, it is escaping into the another medium, and that angle is known as the refraction angle is phi 2. This is the critical angle case where comparatively over here the angle of incidence is higher, and in this case it is the angle of refraction is exactly 90 degree, or it glazes the interface between these two mediums. So this, in this particular case, the incident angle is known to be the phi c, the critical angle. If any incident ray exceeds this angle phi c, then it will become total internal reflection. Okay, so this is being referred by making use of the Snell's law. The Snell's law states that the ratio of the sines of the angles of incidence and refraction is equivalent to the ratio of the indices of refraction. So indices refers to the refraction index. Now the angle of incidence is considered as phi 1 is related with the angle of refraction phi 2 using the Snell's law by making use of the formula n1 sin phi 1 is equal to n2 phi 2 into sin phi 2. Now here we can clearly observe this equation is referring to this particular diagram where the angle of incidence is phi 1 and the angle of refraction is phi 2, and there are two mediums. Angle of incidence is taken at a medium having the refractive index n1, and the angle of refraction is taken at the medium having the refractive index n2. Therefore, we are going to have this expression n1 sin phi 1 is equal to n2 sin phi 2. By rearranges this expression, that is taking this sin phi 2 to left hand side and then n1 to the right hand side, we can have the expression sin phi 1 divided by sin phi 2 is equal to n2 by n1. So again, this is also referring to the same diagram. That's why figure A is being represented here. Now considering the special case or the limiting case, that is the critical angle. The critical angle in the sense the angle of incidence is represented by phi c. So compared to this one, phi 1 here is replaced by phi c, and angle of refraction is going to be 90 degree. Angle of refraction in the sense it is phi 2, that will become 90 degree. Now make the corresponding substitutions over here, that is phi 1 is now become phi c. Therefore, instead of this phi 1, we replace that with phi c. So it will become sin phi c. That is what represented here. And angle of refraction, that is phi 2, that will become 90 degree. Substituting phi 2 is equal to 90 degree, we get sin 90, that is equal to 1. Therefore, this complete expression reduces to the sin phi c is equal to n2 divided by n1. So this is what the critical angle calculation or the representation. Now this is a general representation of the light traveling through the core of the optical fiber. So here we can observe, so from this point up to this point. So in between, this is the core region of high refractive index. From this point up to this point, this is the cladding. So one side of the cladding is being represented. So that is of low refractive index. Now the light having incidence angle greater than the critical angle is being considered here, and this is a meridional ray. Now the light is going to hit the interface of the core and the cladding. The angle of incidence is greater than the critical angle, so phi is being represented here. Because of that reason, it will get total internal reflection, that is reflecting back into the same medium. So the same process will continue up to this, and it will and this is how the light is going to travel through the core of the optical fiber. So again, a reminder over here. So this total internal reflection usually refers when the light is traveling from a medium of higher refractive index to a medium of lower refractive index, then only we can achieve the total internal reflection. Therefore, the core will have the higher refractive index and the cladding will have the lower refractive index. Now coming to one more concept called the acceptance angle. Now let us go through these terminologies once and then we'll have the diagram. Now the angle of incidence greater than phi c. Phi c represents the critical angle. At the core cladding interface are transmitted by the total internal reflection. It is clear that not all rays entering into the optical fiber will continue to propagate down its length. Okay, so this is just a basic basic concept. Now the acceptance angle comes into picture when the light entering from air medium to the optical fiber. So that is when a light source or the optical source generates the light, it is not directly into the light will not directly get into the optical fiber. So between the light source and the optical fiber, there is one more medium. Usually that will be the air medium, right? So now entrance from that air medium to the optical fiber must happen at certain angle. That is what the acceptance angle we are going to have. Now let us go through the diagram for better understanding. So try to understand this diagram representation once again. So from this point up to this point, this is the core region of the optical fiber represented here itself. This upper region from this point up to this point, this is cladding. At the lower part, from this point up to this point, so this is the cladding region, right? So this is the light being traveled through the core of the optical fiber. Here, for better understanding, two different rays are being considered. So one is the A and one more is the B. Now here we are going to consider that the light source has generated the light according to the signal, and then that light has to enter into the optical core, and between the light and the optical core there is air medium present. So this is what is our consideration. So now with this case, let us start with the ray A and then we will go to the ray B. Now the ray A is entering this optical medium with certain angle. Exactly it is passing through the axis of the optical fiber. At that it is going to have an interface. Now this one is entering at an angle theta A. Since this is the air medium, this is the optical fiber medium, the glass medium we can consider. The refractive index of these two are going to be different. Therefore, when a ray enters from air medium to the glass medium, there is a slight refraction that is happening. That we can clearly observe. The light ray is not a straight line. Whenever it has got hit to the optical fiber, the axis, then due to change in the refractive index, a refraction is going to happen, and due to that refraction it has got bent to certain extent. Now after that it will hit to the core cladding interface. If the angle of incidence at this core cladding interface is greater than the critical angle, then it will continue to propagate with the concept of total internal reflection, and the same will continue till the end. Now getting into the concept of one more light signal, that is the B. Now B is taking a different angle of incidence which is much higher than A, Now the B is entering from the same point, that's the axis, to the optical fiber. So due to the concept of difference in the refractive index, again it has got refracted. Now after refraction, it can be observed that at the core cladding interface, the angle of incidence at this point is less than the critical angle. Therefore, it has not reflected back, it has got refracted into the cladding medium, and at the cladding medium it will get reflected once again, and eventually the signal will be lost due to the radiation. So it will never enter back into the core of the optic fiber. Now the reason what we have to understand over here is, so from air medium to the optical medium, when the light enters with certain angle, then only inside the optical fiber it will satisfy the criteria of total internal reflection. If the angle of entry over here itself is too high, then it will get lost. There will be no total internal reflection. So now we have to identify what is that particular angle within which we must make the light source to enter into the optical fiber. That particular angle is known as the acceptance angle theta A. So acceptance angle theta A is the highest angle of incidence from air medium to the optical fiber medium, within which, when the light enters inside the optical fiber, total internal reflection can happen. If the angle of entry itself exceeds this acceptance angle, then there will be no total internal reflection inside the optical core. It is not at all possible. So that particular angle is called the acceptance angle. Now the light can enter from this direction or from this direction. So in either side we can identify theta A. That is the acceptance angle. Now the range over which, that is what represented in the dotted lines, the range over which or within which the light can enter into the optical medium and it can achieve total internal reflection inside. So that angle or that overall range, we call it as the acceptance cone. We call that as acceptance cone. So if the light entry is within this range, then we can say, okay, so there is a faithful transmission of the signal inside the optical core with a total internal reflection. Any light entering beyond this cone, then there will be no total internal reflection. Instead, it will be refracted and eventually it will be lost. Therefore, the acceptance angle is represented by the term theta A. Okay, now what all I explained in the previous slide, all of them are being represented over here. Just a glance again. So two rays are considered, A and B. So starting with the ray A. So ray A enters the fiber core with an angle of theta A with respect to the center of the axis of the core. So that you have to consider. The ray A refracted at the air core interface before transmission to the core cladding interface at the critical angle. It gets total internal reflection and transmitted through the fiber. Coming to the ray B will not satisfy the criteria and it will get refracted to the cladding and eventually it will be lost. Now at the air core interface, that is what where we have to identify the angle theta A, the acceptance angle. Ray greater than acceptance angle theta A will be lost. It must be within the range of acceptance cone for total internal reflection through core of the optical fiber. Right? And the last point is going to say that at the entry of light from air to the optical fiber, so it has got refracted to certain range. At the receiver side also, when the light has to come out of the optical fiber back to the detector, again there will be intermediary air medium is present. Now at the entry point, how much angle it has got refracted, at the exit point also it will get refracted by the same amount. So that's what the symmetry consideration we are going to have in the third point. Thanks for joining.